Hey class, it is Mr. Shrum again. And in this tutorial, we're going to look at waves. So this is all an introduction to waves. And we're going to define the wave, try to distinguish between mechanical and electromagnetic waves, and then describe transverse and longitudinal mechanical waves. So let's get into the intro. All right, so we're told to picture a crowd at a football game doing the wave. A group of fans stand up, raise their arms above their heads, and quickly sit down again. And this action is repeated by successive groups of fans, so one after the other, around the entire stadium. If the fans have good timing, the result is a wave or a ripple that travels through the crowd. Although no one in the crowd is actually moving away from his or her seat, this up and down wave motion moves around the entire stadium. And we encounter these types of waves all the time in everyday life. We see stadium crowds doing the waves. You see the ocean or water, lakes. You see ripples in a puddle when raindrops are falling. We see ripples move across a flag as it flutters in the wind. And there are also waves that we can't see, such as sound waves, radio waves, microwaves, ultraviolet waves from the sun, and even earthquakes. They move in wave formations, and we'll look at that in the lesson. And here we're going to explore the basic features of a wave and learn how to identify, compare, and contrast different types of waves. So first of all, what is a wave? What are we talking about when we say the word wave? What similarities do you see between ocean waves and a wave of fans in a stadium? In both types of waves, it is energy that is moving. Waves are moving amounts of energy. The people and the water simply provide the matter through which energy moves. Energy is moving through matter in a wave. This movement of energy is called wave motion, and it's defined as the transfer of energy between 2 points without the transfer of matter. So it's important to note that a wave performed by a crowd is not really a physical wave, since no mechanical energy is transferred from one person to another. It is a good model for our visual minds to look at. Let's consider some other examples of waves. In an earthquake, stored energy in Earth's upper mantle is suddenly released, creating vibrations on Earth's surface. However, the layers of Earth through which the energy waves travel may experience no total displacement. Likewise, sound waves from a speaker travel to our ears through air. Air molecules pass the sound waves along until they reach us. But the wave action does not displace the air molecules far from their original positions. The natural world displays an amazing variety of waves with different properties, but they all conform to this very basic definition. A wave is a disturbance that carries energy through matter or space. That's a key point. Even though all these things may look different and they have different properties, they are all disturbances that carry energy through matter or space. Mechanical waves, such as water waves or sound waves, transfer energy from one point to another through particles of matter. This matter, which transmits the wave, is called a medium. So the thing that is actually doing the transmitting is called a medium. And that medium acts as a pathway for a wave to travel. So for example, water is the medium through which ocean waves travel. Air is the medium through which sound waves travel. And Earth's crust is the medium through which earthquake waves travel. And the medium can be solid, liquid, or in a gaseous state. So whatever the wave is moving through, that is called the medium. Next, let's examine how a wave propagates. Propagates means moves, and that's just a fancy term for a wave moving through a medium. For instance, a wave can travel through a loose spring. When you jiggle the spring from one end, the coil nearest the source of movement pulls or pushes the adjacent coil, moving it. The second coil moves the third, and the third moves the fourth, and so on. So in a very similar way, a medium such as water or air consists of particles that interact with each other to transfer energy. When a force causes a disturbance in the medium, the particles nearest to the source of disturbance begin moving. And then in turn, they push or pull against other particles right next to them or adjacent to them. And that transmits the motion. Note that particles vibrate at their respective positions. They're not displaced permanently. Just as the coils of a spring finally return to their original positions, or as individual spectators doing the wave at a football stadium get up and sit down without moving away from their seats. The average position of the particles of the medium remains the same while vibrating. So although a wave appears to be moving from one point to another, the matter in the medium does not travel from the beginning to the end. Only the wave energy does. Matter serves purely to transmit the wave and its energy. All right, so testing your understanding so far, which statement about energy transfer in a wave is true? Particles of the medium absorb energy from the atmosphere. Particles move from one location to another, carrying energy over long distances. Energy is transferred through the interaction of a medium's particles. Energy moves between the particles of the medium. So which one do you think it is? Well, particles of the wave medium interact with each other and carry energy. So it's that interaction that transfers the energy. Here we have a video, and I'll upload this to the Canvas page as well. Here, I'll download it right now. And you'll see wave motion and different types of waves. And in that video, watch how waves behave and follow the movement of energy through the wave media. Media is the plural form of medium. Fun fact. So medium is one, media is two or three mediums. But I don't think I can show this video in my video. I have to upload it to the Canvas. But all it is showing you how waves are actually moving. And in it, there's this orange dot moving along while you're watching the wave. And it's going to move perpendicular to the wave's movement. So a wave may move this way, but you see that particles are moving up and down. And that'll make more sense after you watch the video. In the video, a red ball representing a particle of the wave medium was set on a coil of a loose spring. How did the ball move in relation to the wave's movement? The red ball moved in a direction parallel to the direction of the wave. So sometimes you see that particles are moving perpendicular to the motion or parallel in the same direction. So how do we classify waves? And that ties into the video. But the direction in which the particles of the wave medium move in relation to the movement of the wave itself, and whether the wave must travel through a medium or can travel through empty space. So using those two classification characteristics, let's look at the two types of waves. Transverse and longitudinal waves. So first of all, we're going to look at transverse waves. Recall that the first wave in that video, the orange dot representing a particle in the wave medium, vibrated vertically as the wave moved through the medium horizontally. A wave like this, in which the particles of the medium move in the direction perpendicular to the motion of the wave, are called transverse waves. So look at this. The waves move this way. The wave is moving this way, but each particle is only moving up and down, right? The wave moves this way, but the particles are moving up and down. That is transverse. And some examples of transverse waves are seismic waves, those are some earthquake waves, and then transverse waves are light waves too. To observe transverse waves, try dropping a pebble into a pool of water. Once the waves start forming, gently place a ping pong ball in the water. The ball will bob up and down. That is, its movement will be perpendicular to the movement of the waves, which move outward. And this is an example of a longitudinal wave. So we have transverse, where the particles are moving up and down, yet the wave moves this way. Now we have the wave moving this way, and the particles are also moving in the same direction. And a good example of that is a slinky or some type of coil. You see how there are areas where they compress together and then where they are more spread out, and that is called rarefaction and then compression. So in the longitudinal waves, in the second wave type presented in that video, there is a red ball representing a particle in the wave medium of the spring, and it moved parallel in the same direction as the wave itself. Waves in which particles of the medium move parallel to the wave are called longitudinal waves. Individual particles of wave medium vibrate back and forth to transfer energy. A good example of longitudinal waves is a sound wave traveling through air. In a loose spring-producing longitudinal wave, there are regions where the coils are coming together, right? Compressions, and then where they are more spread out, rarefactions. Rarefactions. So rarefactions are where that's spread out, and then when it's close together, it compresses. And similarly, in all longitudinal waves, there are regions in the medium where the particles cluster together. So particles get bunched up, and then there are areas where particles are more spread apart. And here we can watch some animations. So here we go. sharing this right screen. Okay. So here we have longitudinal and transverse wave motion. Mechanical waves are waves which propagate through a material, medium, solid, liquid, or gas at a wave speed, which depends on the elastic or inertial properties of that medium. So we'll understand that in a minute. But right now, let's focus on this, the two basic types of mechanical waves. The first one, here we go. Longitudinal. The particles are moving very slightly, but the wave is moving along. And you see these particles are moving back and forth in the same direction. And the P waves, or primary waves in an earthquake, are examples of longitudinal waves. When a P wave earthquake moves, it travels with the fastest velocity, and P waves are the first to arrive. That's why they're called primary, P. And other examples of longitudinal are sound. Then you have transverse waves. You see how the particles are moving up and down, yet the wave looks like it's moving to the right. The particle displacement is perpendicular to the direction of wave propagation or wave movement. The particles do not move along the wave. They're just simply oscillating up and down. And an example of this is the S waves, or secondary waves in an earthquake. And these are examples of transverse waves. S waves propagate with a velocity slower than the P waves, or primary waves. And these S waves arrive several seconds later. So longitudinal P waves in an earthquake hit first, they're faster, and then you have these slower S waves. Here we have water waves. These are an example of waves that involve a little bit of both. So as a wave travels through the waver, which is a machine that is used to study water waves, you can see it travels in this clockwise circular motion. It's not just left or right or up and down, it's a bit of this waving clock motion. So look at this particle up here. It's moving a lot more than this particle down here. And that makes a lot of sense. If you've ever seen water move that way. Then we have a Rayleigh surface wave. This is another one that has both longitudinal and transverse motions. And this is the particles in a solid through which a Rayleigh surface wave passes. They move in this elliptical path. So less a circle like this and more an elongated circle, like a stretched circle is what an ellipsis is. And they are different from surface waves in water in very important ways. So these move in a counterclockwise motion. So they're going the other way while water moves in a clockwise, the way a clock runs. And this motion is often referred to as being retrograde, since at the surface, the horizontal component of the particle motion is in the opposite direction as the wave propagation direction. I've identified 2 particles in orange in this animation. This is speaking from the website Maker. Look, it's the waves moving this way, and yet the particles are moving counterclockwise. It's very strange. And these are waves that cause the most damage during an earthquake. They travel with velocities slower than S waves and arrive later. But they have larger amplitude, meaning the particles and the surface is displaced more. There's more movement going on altogether. And these are the ones that you can easily feel during an earthquake. And they involve both up and down and side to side motion. But yeah, it's a fun animation. So let's get back to our tutorial. Now we're going to talk about earthquake waves in detail. It may surprise you to know that earthquakes are an everyday occurrence. Usually they're small enough in magnitude to go unnoticed by us humans. Earthquakes, like so many other things in the natural world, are a manifestation of waves. And these waves are called seismic waves. Any event that causes seismic waves to travel through Earth is termed an earthquake. Seismic waves are mechanical waves that travel through Earth. And they're classified as either body waves or surface waves. Body waves pass through the interior of the planet. Surface waves travel on the surface. Seismic body waves are of 2 types: S waves, which are transverse waves like we talked about, and then P waves, which are longitudinal. Both waves travel using Earth as their medium of propagation. That is the medium through which they travel. And they can exhibit both of these forms. Longitudinal P waves travel a little faster than transverse S waves, and they can move through solid, liquids, and gases within Earth. S waves can move only through solids, so that's important to note. The difference between the 2 waves can be used to detect the epicenter, and that is the point of origin of an earthquake. Because P waves travel faster than S waves, we can determine how far away the epicenter is by calculating the difference in time it takes for P waves and S waves to reach an earthquake detector. And that detector is called a seismograph. And that can be seen here. To find the estimated location of the epicenter, wave distance is compared from 3 or more measurement points. A circle is mapped out from each detector site with the radius equal to the calculated distance to the epicenter. With 3 or more observation points, these circles will all intersect at the epicenter. So here's a good visual aid to show you the difference between transverse and longitudinal waves. It shows you the direction of particle motion, prominent features like crest, troughs, or compressions and rarefactions, and then the examples. Transverse waves are light waves and S waves. Longitudinal waves are sound waves, and earthquake P waves. This is an activity with a wave simulation. Let you guys complete that on your own. And then after that, we are asked another question to check your understanding. Which statement best describes a transverse wave? Particles of the wave medium move perpendicular to the wave. Remember, that's a transverse wave. And then I will come back to this tutorial and talk about electromagnetic and mechanical waves, and then get on to the next lesson. So until next time, have a great rest of your day and good luck with all of your classes, and welcome to second semester. So see you guys later.